And then, so you'll have those two quizzes on Wednesday. And then, also Wednesday, Wednesday's gonna be a busy day. Wednesday, I think I did I send you the email about the review session or no? No? Okay, so I think I will do a review session on Wednesday, because we haven't had one yet at all, right? Because last week, because of the holiday. So we're behind one, and, I think if I did everything Friday, that's gonna be maybe a little bit too much to do like a 3-hour thing on Friday, right? So maybe doing like a Wednesday, Friday type of thing. So it'd be Wednesday after your class Wednesday. For about hour and a half, something like that. I don't wanna go beyond an hour and a half, so like hour, 15 minutes, something like that, if you're interested. I think, since you're already here that day anyway, right? I just thought it'd be more convenient, especially for you guys, more so than my afternoon class. So we'll do, probably the LUN on Wednesday, and then Friday we can do whatever we've got for the kidney. I think that'll work a little bit better, because I think it's too much overload if we did all the review session, everything on Friday for 3 hours. Okay, but I'll send you a message, by tomorrow, just to remind you. Okay, so we'll probably do it after lecture. I'm hoping we can start your regular lecture early, and then I can start that review session like around 7-ish. But then that means we have to start lecture by 5:30, right? Yeah, more or less. Because this week's lab didn't last very long. So I think we can probably start our lecture at 5:30 and then start the review session at around 7-ish. Because I told my other class probably around 7-ish. Okay, but we'll play it by ear, we'll see how it goes. Okay, so I think, we'll do that, okay? All right, any questions on anything? Okay. So we started this chapter already, and we got, like I said, to the first 10 slides for the notes part, but just to review real quick, with the kidney, a lot of anatomy on this, right? And gross anatomy is large, right? The opposite of microanatomy. This is like macro, I guess, macroanatomy. Remember we talked about if you can slice the kidney, like do a coronal section and lift the top part off, you'll be able to see the outer part that we call the cortex, right? The renal cortex or the cortex, and then the part that's deeper, kind of going to like where the renal pelvis and the ureter are at, that's called your renal medulla or just the medulla, right? Not to be confused with the medulla oblongata, the brainstem, right? That's different. Because people sometimes like, that's the same thing. No, these are two different organs, right? One's the brain, one's the kidney. But I think medulla means middle or something like that because it's going deeper in, right? Okay. And then we also talked about the pyramids, right? Like the renal pyramids, and then in between pyramids there were columns. So it's kind of like this. They're kind of like upside down pyramids, and then you have another sort of, I guess you can call it consecutive one, but inside here in the middle, this is what you call your column, right? Column, and this is the pyramid. And this has that pattern in the medulla, that is, of alternating pyramids and columns. Like you see here, this darker red, that's your like the pyramid, right? It kind of looks like a pyramid too, right? And then here, the lighter part in between the other pyramid, that's your column, another pyramid, column, pyramid, etc. Right? And in the pyramid, what you find here is what? What are these yellow things? Nephrons. So in the pyramid, this is where you find the nephrons, right? And then I think there's a better slide to show you in the columns, you have blood vessels. That's where you have the blood vessels, and in the pyramid, like we said, you have nephrons. So remember, the kidneys have to get a blood supply, and they're filtering blood as well. So O2 is being delivered to them, and the blood is also being cleaned. Okay? So again, that's kind of the difference between pyramids and columns. But again, what they have in common is that they are found where? In the medulla area, not the cortex. Okay. And it's really, let me clarify a little bit better with in terms of the nephron, it's really the loop of Henle part. Because in the cortex, technically speaking, you do have part of the nephron. In the cortex part, which is this lighter part here, and then I'll show you later in another slide, this is where you have the PCT and the DCT located. I think there's a better picture somewhere in here, where is it? I have to look for it. Well, even here, like they're telling you, because here, this is telling you that this top part here is the cortex and here's the medulla. So like I told you, yeah, the renal corpuscle and the PCT and the DCT, yeah, they are found in the cortex, and then the loop of Henle, right? LH loop of Henle that contains the medulla. Okay? But for sure, the loop of Henle is found in the pyramid part. Okay, and the cortex is just like these blood vessels. Okay. And then we covered all of this in terms of the parts, like the anatomy of a nephron. That's the one I drew back there on the board, right? So if you could practice drawing that, you know, in a very simple laid out like I did last week for you, that'd be a really good idea. I did put it up because I already had put it up for you last week, right, last time that we met. But again, it's just a very simple, you know, it doesn't even take more than 10 seconds, right? You have Bowman's capsule, right? Kind of looks like a hand, like a mitt or something, and then you have the, what's this that I'm drawing? PCT, and then it starts going down. So this is my, obviously my, what is this versus this arrow? This bottom is thin segment of the ascending line, obviously thick segment of the ascending line. Here is DCT, and then here, your collecting duct, right? And that's kind of the path of everything, kind of starts getting filtered here, where all these particles end up coming here. And we know this process is called what? Filtration, right? Then everything ends up here, and it's just start, if you follow the arrows, just start going down, and then go back up, and then up, out here, right, to the minor calyx, minor calyces, and then that dumps into the major, and the major calyces give rise to the renal pelvis, right, which empties into the ureter. That's all anatomy, you know, and stuff. So this first half of this PowerPoint is pretty much all anatomy, right? And the only thing that I haven't drawn in here are all the blood vessel stuff, right? Again, coming in here, what is this one here? Afferent arteriole, right? And then it ends up in here inside of the Bowman's capsule, right? So what is all this tangled mess here? Glomerulus, right? Or they call it glomerular capillary, same thing. But they're basically capillaries, right? And then the blood vessels leave the glomerulus, and they're called now what? Efferent, right? E for exit. Efferent arteriole. Arteriole. And this one over here we said was afferent, right? A for right. Afferent versus efferent arteriole, right? And then remember now this efferent arteriole is gonna stay close to the PCT and the DCT, right? Gonna stay close to it, but at some point it's gonna dip down into the medulla, right? And it's gonna basically parallel this purple loop of Henle, right? Okay. Again, I'm just tracing the path of blood. It's kind of going like this, and then eventually it's going down. And then you have an upswing of this, and so forth, right? Kind of, again, like I said, mirrors and parallels the loop of Henle in terms of direction of things. But here, in the purple, the stuff that's in here, in these tubules, because this is a tubule system, because we're talking about the nephron, what do we call these red dots that I'm drawing in here, the tubular system? What is it? It's called filtrate, absolutely, yes. It's not called urine until we get to the collector. Okay, so this is filtrate in the tubules, right? And then obviously what's in here? In the red. That's the things that are in here. These are not, this is not called filtrate, but in here you have blood, right? This is blood in here. Because remember, this came from the efferent arteriole. All of this is your vascular system. Afferent arteriole leads to glomerulus. Glomerulus leads to efferent arteriole. And then this top portion here that's kind of hugging the PCT and DCT. Remember we call this, I think I told you last time, we'll cover it again a little bit later, the peritubular capillaries. These are peritubular capillaries. Peri means to surround something. And it's surrounding the tubules. Which tubules? The DCT and the PCT. PCT and the DCT. That's why it's called peritubular capillaries. And if you follow this, then the peritubular capillaries go down into the medulla, and they will change names, and I'll talk about more of this in detail. I'm just giving you a preview. These peritubular capillaries in the medulla are now called the vasa recta. I call them VR sometimes, the vasa recta. So vasa recta are peritubular capillaries, except we call them differently when they're in the medulla, right? So if I were to ask you, where do you find peritubular capillaries? You find them in the cortex. Where do you find the vasa recta? In the medulla. Okay, that's the difference, is location, where they're at. Okay, but we are going to spend some time today talking about concentrations of the filtrate as you go deeper into the medulla. Here, the things that are in the tubule, in the loop of Henle. And we're also going to end the lecture by talking about the concentration of things that are in the blood as blood is decreasing down into the medulla as well. So we're going to talk about concentrations a lot, how things become, generally speaking, more concentrated the deeper you go into the medulla. It's going to get more and more concentrated. In the loop of Henle, in the medullary space here in the medulla, and also in the vessels, such as the vasa recta, how everything is kind of layered out. It becomes kind of less concentrated, more, and as you go deeper in, you get the most concentrated. And it's about things moving in and out, and also water moving in and out, okay? So for the most part, big picture, let's say I have a tube of particles, right? I have some sort of tube, there's particles in it. How can I dilute that concentration within my tube? Where's this tube? Now I'm trying to get it out. This tube. There's stuff in here. How do I dilute what's in here? By doing what to it? Adding water. So if I can get water, this is porous to water, and water is allowed to come in, then the concentration in this tube is dilute. How do I get it to be concentrated? Remove the water, take the water out. So basically water has to be allowed to go in and out of this tube in order for me to either concentrate it or dilute the content that's in here, right? And this is going to be the same concept for these things here, when we talk about in a couple minutes about the concentrations of the filtrate here in the loop of Henle and the concentration of the blood in the vasa recta. Things are going to be moving in and out. Right now, I just give you the example of water, but also what can happen. Break this thing. Also, what can happen in addition to water, some particles themselves maybe are able to go in and out, like salt, like sodium, maybe can go in and out. So another way to make this more concentrated is, you already told me, to take water out, but also to put sodium or other solutes in, right? You can make it more concentrated as well. To make this more dilute, yes, you can add water, but what else can you do to make it dilute? Remove the solutes, right? It'll make it more dilute. So you kind of have to keep that in mind, that something that's concentrated is the opposite of being dilute. They're opposites of each other. Okay? Okay. And this is your typical setup. Here you have the nephron here in yellow, but you also, I like the picture because you also have all of the vasculature, the blood vessel stuff that surrounds things, right? Because these are capillaries, right? Look, and I told you they're called peritubular capillaries when they are found in the cortex, and that's all this stuff up here. Well, they're pointing to it, right? They're pointing to all this stuff that's up here, because I think the cortex ends, if you can see, it ends like here. This is the division. Here up here is the cortex, and here is the medulla. because I think this is a darker red and it's kind of faint line. I think this is supposed to represent the border. This is the cortex. So indeed, you know, the peritubular capillaries are in the cortex, and then here, oh, they even named it for you. I told you, it's called the vasa recta. Is here where? In the medulla. And I told you, right, the vasa recta is parallel, it's hugging the loop appendix, right? Here they're probably drawing you a more accurate one, but later on the cartoon drawing one is more simplistic than this one. But basically, you get the point. And look, you can follow the direction of things. You know, this is telling you the direction of how blood is traveling through the vasa recta, then it turns around and goes back up. Kind of the same thing that we're gonna see with the loop Henle. Things going down, and then on the other end, they go up. Yes?
Will the direction of the blood flow like matter later on? Because you drew it going the other direction.
I know, I was gonna say, that's a good question. So, the direction of the blood flow, in a way, doesn't really matter. It just depends how you draw the picture. Like, cause I think when I drew my picture last week for you, on this side, by the descending limb, I think I had it ascending, right? So it just depends how you draw it. It's not important in that sense, as long as you kind of understand what's leaving the descending vasa recta or what's entering, and vice versa. On the other side, what's entering, what's leaving. Otherwise, it's arbitrary how you draw. It doesn't matter at all. Okay? A good question. Okay. So I think this is where we left off, right? Okay, so this is slide 11.
We did slide 11 and 12.
Oh, we did 11 and 12 already? Okay. Let me just recap this one real quick. Okay. So we did, if you have, I think I gave you a handout for this. If you have a black and white one, or you can refer to the colored one on Canvas. Color does matter because, again, you need to know what thing is being moved actively and what thing is, and how is it being moved actively or passively. So this has to do with movement or transport. Movement / transport of things, right? So we're saying things can move either or be transported actively or passively, right? And here the purple versus the red arrows are telling you this, right? And then remember I told you in this picture, they didn't draw the vessels, and I guess it's okay to not draw them. They're kind of assuming that you understand that the top row, let's say in this box here near the PCT, this top row, 5 things here, these top row of arrows, what you have to look at is they're leaving the tubule, right? And then hypothetically entering a blood vessel, right? Because if they're leaving the tubule, for a while they are, for a moment they stay in the interstitial tissue here in the cortex, they stay here, but they don't stay there forever. That's just temporary because they have to make their way to a blood vessel, right? Because I told you, big picture is that things move either from the nephron tubules to a blood vessel or vice versa, from the blood vessel into the nephron tubules. It's like a two-way street. Things are going back and forth, right? So here in this picture, they're assuming you understand that it's moving into a blood vessel, even though they didn't draw it here for you. Because it's not gonna stay here, right? It has to go somewhere, right? And then by definition, we said that things that move from the nephron tubule into the blood vessel, is that called secretion or reabsorption? Reabsorption. I told you those 3 words, you have to know them very well. Filtration, secretion, and reabsorption. Otherwise you can't answer the question, right? Easy to remember, right? I try to help you to understand that reabsorption begins with the R and recovery also begins with the R. When you recover something, that means you keep it in your body, meaning you keep it in your blood vessels, right? Because remember, things that are in the tubules, you're gonna eliminate them. It's gonna end up as urine. You're gonna urinate them out, right? So if the particles stay in the tubules and remain there and do not get reabsorbed, you're gonna get rid of them, right? You're not recovering them. If you reabsorb them, are you gonna get rid of them if they stay in your blood? No, because you kept them in your body, right? So to me it makes sense. Reabsorption means to recover, to keep something. That means you're not gonna get rid of it, okay? Okay. and it's going into the blood vessel. What's the name of this blood vessel, by the way, that you find in the cortex that hangs around the PCT and DCT? Peritubular, it's this guy, peritubular capillary, absolutely, that's your peritubular capillary. I'm just calling it a blood vessel. Okay, but that's your peritubular capillary. You have more out here as well, right? And again, this bottom row, again, you have to assume there's another blood vessel or whatever, but things are going into the tubules. So obviously they had to start off in the blood vessel, right? They went from the blood vessel into the cortex and now back, and then now into the tubule, nephron tubule. So this is now not reabsorption, but secretion. And you're gonna get rid of it now. Okay? Alrighty. In this picture in white, you have 7 different things. I told you this got cut off. There should be salts. I don't know why I did that. Glucose, and then some drugs. Anyhow, these things that are here in white, these ions or these other molecules, they're 7 distinct ones. There's 7 total. Okay? Some of them are repeated and so forth. I think the things that happen at the Lupa Henle and the collecting duct are pretty easy to memorize. Most of this is salt, right? Salt here at the ascending Lupa Henle, salt here at the reabsorption, that is. Because remember, there's also a blood vessel here, right? What blood vessel am I drawing? Vasa recta, very good. This is the VR, vasa recta. Remember, this sodium that's leaving the tubules and entering the vasa recta, again, that is reabsorption again. So all of this is reabsorption of sodium, right? Either active or passive. You can tell by the different colors here. Active at the thick, passive at the thin. We'll talk about that more in detail later, but where was I going with this? Oh, a lot of sodium, there's some water, urea, but most of that action is up here, right? At the DCT and PCT. People ask me, do I gotta know what, is it being reabsorbed or secreted? Yeah. Well, I know it's a lot of them, there's 7 of them. So what I kinda did, and I did it on the back board, I kinda organized it as a Venn diagram a little bit, and there's 7 different things. So the Venn diagram on the left, starting with that one, right? You have things that are moved actively and moved passively, or sometimes they're moved both actively and passively, right? So how you read that under the active, hydrogen, sodium chloride, and nutrients like glucose are transported actively, right? And passively it's ammonia and water, and the ones that are both active and passive are bicarb and potassium. Okay, I'm looking at the 2 white boxes on this picture here on the board. Okay, I'm not looking at the stuff on the Lupa Henle or collecting duct. Okay, the middle one, who's being secreted and who's being reabsorbed. Hydrogen ion is always secreted. Ammonia is always secreted, right? Both is going to just be potassium and then the other bicarb. So sodium chloride, water, and nutrients. So I have that all correct. Yeah. And then where, in terms of the PCT and DCT, the things are moved, a lot of them, they're moved in both places. PCT and DCT, they repeat them, but the one that's only exclusively in the PCT that's transported is the sodium and the nutrients, like glucose, right? So I don't know if you have a better way of learning it, but if that's helpful, you can use something like that. Okay, because you will have to know how things are moved. What I probably will do, I will draw a picture by hand on the exam of a nephron, and I will ask for you maybe to tell me, for example, I don't know, hypothetically, I'll make something up. Show me where sodium is reabsorbed passively. You have to put an arrow to the part of the nephron where that happens. So you kind of have to know this in order to do that, right? So if this helps you to memorize or to understand how things are moved. Okay, but it's really not that bad. It's just this is the hard part up here. Again, the collecting duct and the nephron are really easy. It's basically a lot of water and sodium. Okay, it's what happens at the PCT and the DCT that it gets a little bit a lot, you know, because it's 7 different things, but if you count, everything should be, add up to 7. Oh, 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7, yeah. In each of the 3 Venn diagrams, there's 7 things. Those are the 7 individual things that are handled at the PCT and the VCT. Okay? Okay, and then we went through this one already too, right? We said? We did? Yeah, okay. Again, how things are reabsorbed at the PCT. And this was showing you sodium and glucose, right? So again, sodium, they're calling it sodium chloride here, but it's the same thing as sodium, right? We say that it's reabsorbed, how? Actively, right? And we said glucose / nutrients, because nutrients is glucose. It's also reabsorbed, how? The red arrow, actively. Remember the picture showed you how all of that happens, right? The active part here was for the sodium, right? Sodium moves in here, the purple dot is sodium, right? It's moving, actually it's moving with diffusion, and then the glucose, the blue dot, this is actively. What does actively mean when I'm moving something actively? Moving it from high to low or low to high? Low to high. Because passive means high to low. So actively it means low to high. So yes, glucose is moving low to high. So that explains the active transport according to my arrow, red arrow, for nutrients. And then the active part for sodium is down here with this sodium potassium pump, right? Where the sodium is moving against diffusion, right? So that kind of proves what this other previous picture was saying. Okay, and this again tells you what happens on, what's present, what type of transporter is present on each side of those cells, right? The apical, the one facing the lumen, and then what's on the basal side of it. Okay, now remember I told you if at least one step is active, then the overall process is active, right? Because we're not saying each single step is active, right? Because the movement of sodium and heat into the cell is not active, but down here it's active. So by default, the process of taking sodium from out here into the lumen into the blood vessel is still active. We're calling it active, right? And again, if sodium is here in the lumen and it ends up in the blood vessel, that is called reabsorption. We're recovering it. Is this gonna get eliminated if it's in here? No. Almost did, but it got recovered. Changed its mind, says I want it back. Right? Okay. Okay, so is this where we officially left off? Kind of, sort of? Okay. After 30 minutes, that's fine. But I think that's how much it took to do that class too. Okay. So we're talking about the countercurrent multiplier, and the countercurrent multiplier occurs at the loop of Henle. L of H, or LH, loop of Henle, which is what you see here in yellow. Okay, the loop of Henle. And again, the lighter pink is your cortex, darker pink is your medulla. Okay, and here they only drew one capillary here, and this capillary is also better known as the what? Because we're in the medulla, this is your vasa recta again. Okay. Vasa rectas, you're gonna see they parallel the, like I said, like the loop of Henle. So they also have, not a happy face, but it's a vessel. They also have ascending and descending limbs. You know, I'm just arbitrarily, but it goes back to your question earlier, right? It doesn't matter. I'm just making this one. If this was the ascending limb, then this is the descending limb. I could have drawn them the other way. It doesn't matter. But how this one is drawn and set up, because they're showing me that water is entering it, then by default, I have to change colors, too much red. By default, I know that has to be the ascending limb. So blood is traveling this way. It has to be because water enters the ascending part. That's how I know the arrow is going, blood is going up this way. That's this one, that water is entering here.
So water only goes into the ascending part of the vasa recta?
It enters the ascending. Water can enter the ascending, yes, absolutely, but it leaves, but it can leave, and I'm gonna get to this toward the end, it can leave the descending and re-enter and the ascending. This water, this Greek water that I have here, this came originally from the vasa recta. But I can have another water, and let me do it in a different color, just to show you, it's still water, but it comes from different sources. This water over here, maybe for example, is still gonna enter the ascending, but this water is from the descending loop of Henle. This water. But the bottom line is the ascending limb accepts water. Water likes to enter the ascending limb of the, this red is the vasa recta. I'm getting ahead of myself because we're all talking about the vasa recta, we haven't even talked about this one yet. Okay, but this is the vasa recta. You still have to know it, but let me go back before I get too further ahead. And I'll come back to this picture. But this is the vasa recta, right? But let's talk about the loop of Henle because we're kind of now scattered all over. Okay. We're at the loop of Henle. Remember again the Bowman's capsule, whatever was here, right? Proximal convoluted tubule, and then now we're entering here, right? The filtrate now enters here. And it starts relatively dilute. I know I scratched it off, whatever. 300 milliosmol. Milliosmol is the concentration, right? Whatever. I'll write it right here for you. 300. And as I'm going down further and further into the medulla, these numbers are increasing. You don't have to memorize the numbers. That's not important, but look at the trend. What can you tell about the concentration inside of the filtrate inside the loop of Henle as I'm going down? It's increasing. The reason why it's increasing is because what's happening to it? The clue is right here. Water is leaving it. So of course it's gonna get more and more concentrated the more and more water leaves. And you kind of reach a peak of about 1200 milliosmoles where it's super concentrated. Because all the water left the descending, so this is called the descending loop of Henle. And that's a unique characteristic. They're telling you right here that the descending limb is permeable only to water. The solute, like salt, is not allowed to leave. Water is the only thing that can leave, and water will leave. I haven't told you why, but water will leave, leaving behind the salts, or any particles, so that's why it gets concentrated. So on the next slide, I explain all of this in words. I think I have 2 slides that explain all of this in words. Yeah, 2 slides that explain this in words. So I like to just do the picture part first. Okay, so you're with me. The descending loop of Henle is permeable to water, so water will leave, but impermeable to the salt, so salt stays behind, so it gets more and more concentrated. Okay? Why did the water come out of this thing? We know it's permeable to water, right? But water could have gotten in, water could have gone the other way into it, but if water doesn't go into it, water goes out of it, right? And if you remember anything about water movement, correct, which we call osmosis. Osmosis has to do with water movement. Osmosis. Water moves from, I see what you got. Let's call this better hypotonic environment to a hypertonic environment. Hypo to hyper. Hypertonic environment, right? Hypo means low, right? So maybe I only have 2 or 3 things here, right? But hyper is, when I have a lot. So basically water likes to follow wherever there's a lot of particles at. Okay, that's basically how water moves. Right? Water will always follow where there's something hypertonic. Right? And I think we talked about this when we talked about the alveolus and there was sodium and chloride. Remember the CFTR channel? When all that chloride and sodium was inside the water film, the mucus water film in the alveolus, then what happened? Water will go into it to make it even more watery because we don't want it dry, right? So that's how water works. Water always will follow wherever you have more solids, right? It's like that same kind of explanation I gave you. If you have two glasses of water and they are connected in the middle, two compartments, and this one has many ice cubes in it, and this one only has two, which way will water move? Left to right or right to left? Right to left, right? Because there's more particles here. Remember I told you water likes to follow where there's more, where it's hypertonic. This is hypertonic. And if you don't believe me, take all the ice cubes out, you're only be left with this much water. So you're really moving from high water to low water. All of these ice cubes are taking up the volume of the water, right? So you can kind of think of it that way, right? Basically water likes to follow wherever it is very hypertonic, where it's concentrated. This water is leaving as opposed to entering the descending Lupa Henley because it must be very hypertonic out here. Meaning you have a lot of particles in the medulla, right? Guess what's in the medulla? It's right here. Sodium chloride. It's so salty out here, there's so many things. You have sodium chloride, and later on you're also gonna have urea. All of these particles are making the medulla hypertonic. So hypertonic that it draws the water out of the descending Lupa Henley. It's attractive, right? I told you it goes from hypo to hypertonic. But this water can't stay here forever because it's gonna dilute the medulla. So now this water will enter and be reabsorbed into the blood vessel that we call the vasa recta, because we are in the medulla. And it enters the ascending vasa recta. Because I told you there's an ascending and a descending that we'll talk about later. Okay, so again, you're with me so far, because remember I told you things move either from the nephron tubule to a blood vessel or vice versa, from a blood vessel to a tubule. So, but the middleman, the middle territory is the interstitium of the medulla or even the cortex, but it doesn't stay here forever. This is like temporary. That's like halfway, the journey. You have to complete it and enter something else, right? So again, it's hypertonic because you have a lot of salt that came out of the other end, the ascending Lupa Henley. Let's talk about why salt left in the first place. Ascending limb is very different from the descending because it's the opposite. Ascending is impermeable to water, so water can't go in and out, unlike on the descending. So the ascending is impermeable to water, but this time it's permeable to the salts, sodium and chloride. You see how they're different? Over here, only water is allowed to move. Over here, only salt is allowed to move. So we reach our peak here, right? At 1200, and let's say over here inside the medulla, do a different color. The concentration, the osmolality is about, 900 milliosmoles. So you have higher concentration. This is 1,000 right here. This is 900. So sodium is allowed to move. Is sodium going to go? First of all, is sodium going to go into the tubule or out of the tubule? If you know that sodium is 1,000 milliosmoles out here and 900 here, it's going to want to go out, right? Just by passive, simple diffusion with the sodium channel. It's going to go from high to low. You have more sodium here than you do in the medulla, and you are allowed to move sodium, so sodium will gladly leave passively through a sodium channel. No energy involved. It's moving from high to low, and here you go. Well, they didn't put it in here. This is the thick. I should have put this a little bit lower because this is at the thin. They move passively. I think I have another picture I'll show you later. Or it's in words down here, but I mean, I know I put it, well, I'm sorry. Should I put it right here? So this is the thin segment. At the thin segment, where am I going to write this? Can I write it here? Because you have a thin segment, remember, and you have the thick segment. At the thin, it moves passively. At the thick, it's going to move actively. All of this is written on the next two slides in words. I'm just showing you the picture first. Because otherwise it doesn't make sense, all those words. Okay? But you can see clearly this is thick and this is thin. Okay, but both of them, thick and thin, it doesn't matter which segment you're at, they will move sodium out of the tubule, either passively or actively. You understand why it's passive here? Because you have higher salt in the tube than you do outside. Over here now it's different. Let's say over here, I'll pick this one, it says 600. How about if outside was 700? And sodium is allowed to move. Is sodium gonna move by simple diffusion from 600 to 700? By facilitated diffusion, is it gonna move that way? Passively? No, it has to move actively. Because you're moving now from low to high. So it's gonna require, this like sodium potassium pump. There's some sort of a, yeah, some sort of a pump. Where did I write that down somewhere? It's in here somewhere. I don't have time to look for it. But it's gonna require some sort of energy to move the sodium out, right? And again, the movement of sodium out here into the medulla is what contributes to the hypertonicity of the medulla, which attracts the water on the other end to come out. And again, do you see because we're going up this time, right? Because we went this way, then we went this way, then the filter is going up this way. Do you see as we're removing more and more salt, more and more particles, my concentration is becoming what as I go out this way? More concentrated or less concentrated? Less, because I am removing what? The salts. You understand why it's becoming more and more concentrated as I go down? On this side, it's becoming more and more concentrated because I'm removing the water as I'm going down. So yes, that's why it's becoming more and more concentrated. If I go the other way up this way, it's becoming more and more, it's becoming less and less concentrated because I am removing the salts. So it should make perfect sense to you why it's less concentrated at the top of the loop of Henle and more concentrated as you go deep into it. And the most concentrated is down here. Does that make sense? Yeah? Uh-huh.
So you said that up a thin segment, NaCl will move passively?
Yeah, from high to low.
I think it's actively, so wouldn't that be in both NaCl? The middle there? Or that's just for this part, not for the whole?
So you're looking at the middle Venn diagram?
No, the first one, how it moves?
The first Venn diagram?
Yeah. Would it be both?
Oh, I see what the confusion is. Okay, this, what I drew up here for you, this is only happening at the PCT and DCT. This has nothing to do with the loop of Henle and collecting duct. Because even if you look at the third diagram, Venn diagram, see, I'm talking only about the PCT and DCT. I think I kind of mentioned this was just for the first two boxes. But remember I told you this is slide 14. I told you that this other stuff here is easy to memorize. It's not a problem. This is what's difficult to memorize. This is just for the top stuff. Yeah, I'm not talking about the, otherwise, yeah, then you're right. But no. Yeah, this is just for this is what happens only at the DCT and PCT. Yeah, this stuff is really easy. Okay, slide 14, this is where I was at, okay. And this sodium and chloride that's out here can't stay out here, right? Gee, I wonder where it's gonna enter. Where does it have to enter? If it originated from the tubule, where's it gonna enter? Or what's gonna happen? Where's this gonna go? It can't stay here. Where will it go? To a blood vessel. Again, you have to remember that things move from a blood vessel to the nephron tubule or vice versa, from the tubule into back to the blood vessel. They can't stay in the middle forever. They have to cross it, of course, but again, you get it. If this is my tubule, it can exit and be kind of in the middle of nowhere, but then eventually has to re-enter now a blood vessel, right? You don't leave a blood vessel and then re-enter the blood vessel, otherwise then why'd you leave it, right? Doesn't make sense. If you left the blood vessel, it's because you're on your way to the tubule. Vice versa, if you start off in the tubule, you leave it, you have to now enter a blood vessel. You don't go back from where you came from, right? So again, the sodium, if it started in my tubule and goes out, it's going to re-enter the blood vessel, and what do we call this blood vessel that's around the loop of Henle? The vasa recta, and this time it's going to be the descending vasa recta. That's this one, right? So, salts like sodium are allowed to go in to the descending vasa recta. Yeah, they can't stay there forever. So I think these next two slides pretty much say what I just said, these last couple minutes. Again, the countercurrent multiplier that we've been talking about occurs at the loop of Henle, right? And it's basically responsible for concentrating things, you know, and the whole goal is to concentrate the urine in the collecting ducts, right? And I told you you have these two segments, the descending loop of Henle and the ascending one. And again, how they're different, you know, it's like the bottom of it's right here, right? The bottom of the page, how they're different, who they're permeable to and who they're permeable against. Permeable to water, the descending, but not permeable to sodium chloride. It stays behind, right? And as you go deeper and deeper into the medulla, yes, the filtrate is more and more concentrated because all the water is leaving it. We've talked about that, right? Okay? And then the ascending is the opposite. Water cannot pass into or out of the ascending, right? Water remains there, but the salts can move. And they do leave, either passively or actively, right? Passively is going to be here, like I told you, at the thin segment, and this is where we use sodium channels. And here at the thick segment, they move actively, and it's some sort of, oh my goodness, what are we gonna call this one? I don't wanna call it the sodium potassium pump, because it has nothing to do with the, or does it? Hold on 1 second. Oh, yes it is, I was right, it is a sodium potassium pump. So, by sodium channels, and this one is by the sodium potassium pump. Remember the pump, you require ATP energy, that means you're going from low to high, correct? Okay, so we've talked about kind of those things before. Okay, any questions so far? Right, continuing with the story, I repeated this again, whatever, okay. Occurs at the loop of Henle. Here is just telling you that this countercurrent multiplier, again, that involves the loop of Henle, again, the limbs are relatively close to each other, right? The limbs of the loop of Henle, they're relatively close to each other. Countercurrent because they're going, you know, you have an ascending and you have a descending and you have an ascending, but these limbs are very close to each other because the medulla has to remain hypertonic. It looks like this versus something like weird that would look like this. This is too far apart, because if you don't have to notice it, but if you did it like this would not remain hypertonic for very long. They have to be in close proximity, because it has to be able to reabsorb and move quickly from one area to another. This is too wide. This is not gonna work, but they have to be in close proximity to each other. Sodium chloride moving out of the ascending limb, that's what I just told you right now, that's what makes the medulla hypertonic, but I told you it's not gonna stay there forever, right? It has to go back into the, which one did I write down? It has to go into that sodium has to go back into the descending vasa recta. This raises the filter osmotic the descending limb. Yeah, with the counter, cause we removed all this water, so yes, the filtrate, the concentration, cause osmolality is the same thing as concentration, right? Cause all that water was leaving the descending limb, so of course it's gonna be more concentrated. Right, and then that, that's delivered to the ascending limb, right? So it's very concentrated here, just like it is over here in the ascending limb. And then again, now the sodium chloride starts leaving the ascending limb, which is everything that we've already actually talked about, all this. And if it's more hypertonic, the increasing the hypertonicity here, that's what's gonna in the medulla is gonna cause water to diffuse out, but out of the descending lubricant, further concentrating the filtrate. So it basically says in words, probably a little bit neater than what I just told you, right? So, you know, read it, maybe side by side next to the picture, and I think it'll start making more sense to you. And it's the picture that I think I gave you as well on that one. Maybe I should have put both of them on the same page, or maybe I'll redo the handout for you. The Luther Henley and the vasorecta that I'm gonna talk about in a moment. Okay? All right, and you know, whatever, the number doesn't matter, whether it's 1200, 1400, who cares, but it's just super concentrated when you get here to the bottom of the Luther Henley. Wow, we're still talking about, now we're talking about the thick, okay, which I already talked to you about as well, that sodium chloride does transport that, but it's gonna move, remember, not passively, but actively at the thick, right? Passive at the thin, yes, but at the active, I told you it's gonna be thick, right? And again, why is it active? Because we're moving from low to high. There's lower concentration or osmolality inside the tubule versus the medulla. So it's gonna need energy. It's moving from low to high. And I told you that sodium chloride can't stay there. It's gonna have to re-enter we called it the descending vasorecta, I believe. This is descending vasorecta. Yeah. And here it's showing you now, I'm gonna show you on the next slide, a cell of the thick ascending, right? And it too also has an apical surface that's, you know, facing the lumen side. And at that apical surface, you have this transporter that actually transport three different things, sodium, potassium, and chloride, right? And all of these will, I think I left potassium out, they all move passively with diffusion, from high to low. And on the other side, I'll show you the picture in a moment, you have a sodium-potassium pump and chloride channels, right? And sodium is gonna move against diffusion, and you know that because this is a pump. Remember with the pump, both of these move against diffusion. We learned that in the first exam, right? Remember it was like 2 potassiums and 3 sodiums move both against. So that's the active part, right? And then that sodium that moves out doesn't stay in the medulla forever. It has to re-enter the descending vasorecta. Okay? But again, we're saying sodium moves out actively, right? Because it's moving from low to high. So let's go back here. So I'm talking now about a cell located at the thick segment, right? Where you have sodium moving actively from low to high, from like 600 to 700, right? So sodium at the thick does move actively. Let me go back a couple more slides further. Where is that? Let me start off, I think it was slide 11. Oh my God, what did I do with it? This one. See, they weren't lying, it's right here. Sodium is moving red. Red is what? Active transport. Again, because it's moving from low to high. So we're not lying, right? This has to do because of the sodium potassium part. So let's go back to slide 18, was it? What, this one. And again, as long as one step is active, this whole process is considered an active process. Yes?
So is the apical cell surface a thin ascending limb because it's with diffusion, and the thick one is the basal cell surface?
Ask me again, what?
Can you go back to the last slide?
This slide over here
Yeah, the applicable cell surface.
has this transporter right here,
That's with diffusion, so that's not the thick,
No, it's still, we're both talking about the thick still. But the active part is at the basolateral side. The active part is here, at the basolateral surface. We're still, maybe if I show you the picture, okay? Cause again, we're at the thick ascending limb, right? So we're kinda looking at this cell here. So if I do a cross section, if I were to cut this thick portion in the middle and showed you a cross section, here are all the cells. There's a tubule, right? We're looking here, I draw the lumen too small, but the lumen is here, right? This is the lumen, right? So this is a tube, right? The filtrate is in here, right? It's right here, these are the filtrate, the chloride, sodium, and potassium. So on the apical side, sodium travels by diffusion, from high to low. Now it's stuck here, it's not gonna stay here forever, it has to exit the other end, because remember, things move from tubule, in this case, it's moving from the tubule to the what? What am I drawing here? This is your vasa recta, because they don't stay forever in here in the middle, right? They go from the tubule, through the cell, through the medulla, and then into the vasa recta. And this is going to be the descending vasa recta that sodium is allowed to go in through. So the active part is here, where sodium is moving against diffusion from low to high. And I know it's moving low to high because this is my sodium potassium pump. Remember it needed ATP? To answer your question, this is the active part here.
Yeah, so the apical is what makes what brings the sodium to the.
Yeah, the apical part brings the sodium from the filtrate into the cell, and that's it.
And then it requires active transport.
It actives transport out of the cell into the medulla, and then eventually it has to make its way into the descending vasa recta. Because sodium is getting what? Secreted or reabsorbed? Look where it ends up at. Vasa recta, so it ends up being reabsorbed. We're rescuing it, we're keeping it, recovering it. Get it? Okay. What's gonna eventually follow if all this, if it becomes, let's say, hypertonic in here? Water. Okay. Hypothetically, you take a drug and it stops these chloride, sodium, potassium symporter, or whatever this thing is called. Triporter. Anyhow, it blocks this transporter. So what remains in the filtrate? The chloride, sodium, and potassium is not going anywhere. If sodium, chloride, and potassium stay in the filtrate, what else is gonna stay in the filtrate? Water. And what's gonna happen to all of these solutes in the water? What are you gonna do with them? No. Oh, just, well, okay, what happens to it eventually? I'm pointing down here, so you're gonna pee everything out, right? If it remains stuck in the filtrate, because everything that stays in the filtrate, do you keep or do you get rid of it? You get rid of it. So you're gonna pee out all this water, all these chlorides and potassiums and sodiums out, because you block this. Remember, normally this gets reabsorbed and eventually water is going to want to follow this, right? But if you block this, you're gonna have, you tell me, are you gonna have concentrated urine or dilute urine if I block this guy here? Diluted, because the water stays in here. Water is not going anywhere because these guys did not go anywhere. Remember, water follows and chases things. If no one moves, it's not moving either. It's gonna stay right here, and you're gonna end up urinating all this out. You're gonna pee a lot, actually, right? Have you ever heard of a drug called, they call it the water pill, Lasix, furosemide? People who are hypertensive, have high blood pressure. One way to lower your blood pressure is to lower your blood volume, which means to lose water, to pee a lot. So these people are on these drugs that they always have to go to the bathroom. So how that drug works is it inhibits the chloride, sodium, potassium transporter. It inhibits it, so these solids remain here and also water remains here, and you end up peeing everything out, right? So you lose water, it'll drop your blood volume, it drops your blood pressure. That's how those work. So it works, but it's just you're going to the bathroom a lot. Cause you're not, your urine is very, very dilute, so it's gonna be a very light color instead of a dark color. Your dark color is more concentrated, so it's very dilute urine here. What about in your blood? Is your blood gonna be dilute or concentrated? If your filtrate / urine is dilute, how about over here? Concentrated. I told you things are opposite. If the filtrate is dilute, blood has to be concentrated. You can't have both, it doesn't make sense. Because again, this water would have been coming in here, but it's not coming in here anymore. So all the water remains here. So these people are losing massive amounts of water all the time. I don't even know what slide I'm supposed to stop on. My talking too much. It's really fun, though. I find it interesting. I hope you do, I don't know. Anyhow, yeah, to have the countercurrent multiplier work, again, water has to leave the descending limb, right? And then it has to enter the ascending vasa recta. It has to be removed by the medulla. It can't stay there forever, because you'll dilute the medulla and it's not gonna work, right? Well, it has to remain a little bit in the medulla, but it can't stay there forever. Then eventually it goes into the ascending vasa recta. Okay, which is gonna lead us now, we keep talking about the vasa recta, that's now the counter-current exchange, so it sets up nicely our discussion next, or coming up with the vasa recta. I think I have one more slide before I show you the vasa recta. Additional information, oh god, what else, okay. Yeah, the medulla is very concentrated, right? It has, this is pretty high, 1400. Again, the value doesn't matter, it's not important. But again, yeah, this creates a high concentration. That's what hypertonicity means, high concentration. Why is there a high concentration in the medulla? How is that related to sodium chloride? Where did this sodium chloride come from? We just talked about it. Where does it lead? Ascending loop of Henle, right? And it goes out into the medulla, and that's why the medulla is very concentrated. It's all about the direction, how things move, where they're going, where they came from, where they're going to, and all that kind of stuff, and water, right? And then, like I told you, water's gonna follow that area of high concentration, right? High osmolality, right? But there's a limit to how much water can come out. It depends how concentrated the medulla is, right? So it depends on the salt. So it's actually limited by how much salt is leaving, either how much, by the number of sodium channels at the thin, this is a thin one, thin ascending loop of Henle, or by the sodium potassium pumps, by the number of sodium potassium pumps at the thick ascending loop of Henle. If you don't have any sodium coming, if these things are not working, then no hyperosmolality in the medulla, no water's gonna leave, right? It all depends on these guys, and they have a limit. There's only a certain number of them at the ascending loop of Henle. So that's the limit of how much water. Water just does not have the free-for-all and can as much leave as it wants to. No, it's controlled by how concentrated the medulla is. If it's not highly concentrated, water will not leave. Even though it can, it's not going to. It's attractive, remember again, when you have the most concentration of things, of salts. And again, I already told you that the descending and ascending limbs have to be close to each other. It can't be a big wide view, it has to be, close to each other for this thing to work. Okay, so now we're switching over a little bit and talking about the vasorecta. We're not talking anymore at the level of the loop of Henle. This is at the what? Well, I just gave you the answer, right? At the vasorecta now. Vasorecta, remember, is a blood vessel. It's a peritubular capillary in the medulla. Okay, and again, you can kind of follow it here, and they have two limbs as well. This is the descending limb of the vasorecta and the ascending limb of the vasorecta. Okay, do not confuse this with the loop of Henle. This is not the loop of Henle here. Okay, so if you look here, it's kind of analogous. It's not the same thing. The only thing that they have in common is, remember, kind of behind here is the loop of Henle, because remember the vasorecta follows very closely on top of the loop of Henle, right? This is slide 20. Use that picture out. Here's the vasorecta. This is showing me the descending vasorecta with this black arrow, and this is the ascending, apparently, vasorecta. But you see how it's smothering, it's on top of the loop of Henle, the vasorecta, correct? Because even things from the loop of Henle can make its way into the vasorecta as well, which we're going to see in a second. So let's go back to slide 20. And again, there is a layered concentration. As we're at the top of the as we're at the top of the vasorecta, closer to the cortex area, you see that it's kind of dilute, the blood, right? And as we go deeper and deeper into the medulla, it's becoming more and more concentrated. On both sides, you can do the same thing here. Look, it's at 400 something, and then as we go here, it reaches, 1200. Over here, same thing. It's at whatever, 400, whatever, 300. As you keep going down, the blood gets more and more concentrated. And again, this is all because of water movement and salt/urea movement. Okay? And again, the big picture is here is if you remove water from a blood vessel, it's going to get more and more concentrated inside. Okay? If you remove water, it gets more concentrated. If you add more stuff like salt into it, it's also going to become more and more concentrated, right? If I add more salt, and what if I do both? Add salt and remove water, super concentrated, right? And that's what's kind of happening as you go lower and lower, deeper into the medulla. Okay, so, and these things are conceptual, and if you don't get it the first time, that's fine. I don't expect you to, but after reading, some of the text that I have that follow this and explains everything here, right? So let me explain it in pictures before I start talking about what happens at the descending and ascending segments. Okay, so let's back up with this picture. I could talk about the picture first and the rest makes sense here, right? And this one is a little bit more complicated than the loop of Henle, because the loop of Henle was simple. The descending limb only lets water out. Ascending limb only lets salt out, period, and that's it. That's the end of the discussion for the countercurrent multiplier at the loop of Henle. This time it's the countercurrent exchange at the vasorecta. And it works a little differently, right? And you'll see why it works differently, because on one limb, things are allowed to leave and enter, and on the other one, same thing, things are allowed to leave and enter it, right? So let's look at urea and sodium chloride real quick. So what's happening here is that at the ascending vasorecta here, it's permeable and it lets out sodium chloride and urea. It lets out the particles out, and now they're in the medulla, making the medulla concentrated, but it doesn't stay here forever. It re-enters it at the other end, at the descending vasorecta, right? So you start it here, and then it ends up, and then it's here, and then it ends up here. Water moves the opposite way. Water leaves the descending, it's right here, it's in blue. The blue arrows are water. Water leaves the descending, right? And water leaves the descending because it's salty here. Because it's hypertonic. Remember, water's not going to move for any reason unless it's hypertonic. So water is moving here because it's salty. There's particles from the vasorecta that, from the ascending vasorecta that came out. And remember, there's also salt from the ascending loop of Henle. So yes, water's gonna want to leave. It doesn't stay here forever, then eventually the water re-enters the vasorecta at the ascending vasorecta. So you see they're opposite ways. They don't go the same way. They're opposite. Water and the solutes go opposite ways. But what you do have to remember is that the solutes originate in the ascending vasorecta and re-enter it at the descending. Water is the opposite. Water originates at the descending and enters it at the ascending, right? So if I had to draw this over again, and I like to make things simple, right? If this is my descending vasorecta, ascending vasorecta, water moves this way, and the solutes like urea, sodium chloride moves that way. So I don't know, and to me this is kind of like a counterclockwise little thing. In my head, that's how I remember this. That, oh, solutes they leave the ascending and enter the descending. How about water? Water leaves the descending and enters the ascending. Isn't this like a countercurrent little loop? You just have to make sure the solutes is this line and water is this line, otherwise you mess the whole thing up. I don't know, this works for me if I memorize this picture. Okay, let's explain why, as I'm going down, as blood is going deeper into the medulla, why is it becoming more and more concentrated? First of all, the solutes are entering it, so of course it's going to become more and more concentrated as I go down. Look, all of these black arrows are all entering here, and that's all sodium chloride and whatever, and urea. So solutes are entering, so yes, it's becoming more and more concentrated, but on top of that, what else is happening? What's leaving it? Water. Even more reason why it's becoming more and more concentrated. Does that make sense? This part? So the descending limb is really easily explained why it becomes more concentrated for two reasons. Solutes are entering it and water is leaving it. So of course, it's become super concentrated, the blood, at the bottom of the vasorecta. This one becomes a little bit more difficult to explain, but I'll do my best with this one. With the ascending limb, water is entering it. So what used to be very concentrated as you go up, doesn't it make sense? It's becoming more and more dilute as more and water keeps entering this thing. Not only is more water entering, but who's leaving it? The solutes are leaving it. So it becomes less and less concentrated as I go up. I think this simple little picture is probably the most difficult concept even to understand and to teach of the entire course, is this vasorecta, this countercurrent exchange, probably more difficult than countercurrent multiplier. It is very conceptual. So if you don't give the first time, it's understandable, because you have to understand things are moving in opposite directions. You have to understand what concentrated versus dilute means. If you get it right away, well, that's great, because I know when I studied this, I had no idea what was going on. Yes.
If water follows solute, then why is water going one way while solutes going the other?
If water is following the solutes,
Because isn't there a high concentration of solutes from the right side, the ascending vasorecta?
here,
Yeah, so water goes there, right? So then, but then why does solutes leave?
why are solutes leaving to begin with in the ascending vasorecta? Is that what you're asking?
Okay, yeah, why does solutes leave in the ascending vasorecta?
Because first of all, they're permeable to sodium chloride and urea, and you do have these urea transporters. You do have these urea transporters here that I haven't talked about. Is that coming up on the next couple of slides? Where's the? Oh no. The urea transporters. Where are they? I think that might be on the loop. There's someone here. But anyhow, it is permeable to sodium, but then you can make the argument, so instead of, at the ascending, instead of leaving, why don't they just go in instead, right?
Yeah. Because
See, I told you this is like the most difficult
Because
picture of the whole semester, this one. They're allowed, and both sides, they're permeable to sodium, you know, to the solids and urea and stuff, but, they have to contribute to the hypertonicity here. So it has to come out on one end, and, cause remember, this has to be hypertonic in order to draw water out. If it's not, you never will create like a concentration gradient, cause water again will not move out of the, of the descending Lupa Henley, or even the descending vasorecta if it's not hypertonic. So we have to have the solutes coming out from somewhere, and they come out from the ascending vasorecta. That probably wasn't the best explanation, but that's the best one I can give you, yeah.
But I don't understand the way you're explaining this, the solids have to come out and enter back into the Lupa Henley to then exit through your urine, cause that's where you.
Not the Lupa Henley, you mean this?
Well, no, like, if they would need to leave the blood vessels into the Lupa Henley back out, so they can then.
You mean the medulla? Cause they're leaving here, right?
Yes, that's what I'm saying,
So they're leaving here and entering the medulla? Uh-huh.
So they need to leave the blood vessels back into the, what would it be, the ascending limb, so then we can leave your body when it's in.
And the ascending limb of the Lupa Henley, they're leaving there to make the medulla concentrated. So the medulla is concentrated because there's two sources of sodium, you can think of it this way. One source of sodium came from the Lupa Henley, and another source of the salt came from the ascending vasorecta, to make the medulla salty so that water can want to leave. And water leaves, we know already, from two different places. Water can leave from the descending Lupa Henley, and also from the descending vasorecta. Is that not what your question was, or did I not answer it? Okay, try it again.
I don't know how to explain it differently though.
Okay, but you're saying water is leaving here, right? I'm sorry, water.
No.
So solids are leaving here, right?
Yes.
And they're entering the medulla. So this is the medulla right here. Right now I have the salt here. And then salt is re-entering on the other side.
So the vasorecta is in no way connected to the Lupa Henley?
Is it?
Like it doesn't like do any transportation with the Lupa Henley?
Not really, no. No. This is all like a loop just within the vasorecta itself. This is independent of the loop of Henley. Not this particular drawing is, but this, like this water, like I said, it happens to come from the descending Lupa Henley, but this water could have come from the descending, and here it's coming from descending vasorecta, but it could have come from the, descending vasorecta as well. But this salt right here happens to come from this side. Now, I'm not saying that the other salt that comes from the ascending Lupa Henley, it can also, like, I can have another salt coming in here. This salt came from the, whatever, the thick Lupa Henley. This salt can re-enter, but it enters it only at the descending vasorecta. Salt cannot enter here. Salt is only allowed to leave on this side, but salt is allowed to enter here. So in that sense, they're related.
Yeah, I think I just misunderstood then, because from how you explained it before, I understood that like the vasorecta and the Lupa Henley do those exchanges with the solutes in the water.
They can, like I said, in this case, this sodium that left the thick, this is the thick Lupa Henley, it can re-enter the it can enter the vasorecta, but it's gonna be the descending vasorecta. So in other words, there's two sources of sodium that enter the descending vasorecta. One is from the Lupa Henley, ascending Lupa Henley, and the other one is from the ascending vasorecta, from here. There's two sources of sodium that enter the descending vasorecta. Just like there's two sources of water that enter the ascending vasa recta. One source came from the descending vasa recta, and the other one came from the descending loop of Henle. Remember we said it was permeable to water? This water can come in and enter also the ascending vasa recta. In fact, I already drew it for you. It's like that green arrow. Where's my green arrow? Here it is. This is the ascending vasa recta. This water that came here, but you know you also have water that comes from the descending vasa recta that enters here as well. So in that sense, maybe they are related. Is that what you're asking?
Can you go to slide 10? Cause this is where it kind of asked you before if the blood flow matters. Because in this drawing here, if you see like the capillaries on the bottom, the flow is going the same direction as like the.
That's paralleling exactly
Yeah,
the, yeah.
so that's where I get confused because you're drawing the blood flow going the other direction. So,
As
and you
long,
said it doesn't really matter which way you draw it going, so that's why I think I'm confused on just the flow of the blood.
okay, and again, you know, it really doesn't matter, but if we stick to this picture, cause everything is flowing in the same direction, right? The loop of Henle is going down this way, the filter is going down, blood is going down, right? So let's look at water, for example. Water leaves the descending loop of Henle and it enters the ascending vasa recta. Always, it has to enter the ascending vasa recta. Where's the other picture that I had earlier? Water has to always enter the ascending vasa recta. The ascending vasa recta accepts only water. See, right here, ascending vasa recta only accepts water coming into it, not the descending, right? Only the ascending vasa recta is allowed to accept water. So that one, slide 10 was it? So then water would have to enter from the descending vasa recta into the ascending vasa recta, which would be this side. Yeah, water from the descending loop of Henle, sorry, same thing. Water from the descending loop of Henle enters the ascending vasa recta, and also from the water from the descending vasa recta enters the ascending vasa recta. So now we're drawing that, you know, it just depends, cause now I have the ascending vasa recta on this side and not over here. So you see it's kinda arbitrary, it doesn't matter, as long as the water has to enter the ascending vasa recta. No matter where I put the ascending vasa recta, water has to enter it.
I think you got confused because in most of the pictures you did, you always put the glomerulus on the left. So you were making the blood go that way, but
Mhm.
it would like in the other direction.
It's arbitrary, it's just in my head that works for me, that drawing works for me. As long as I know, again, that water is going into the ascending vasa recta and the solutes are going to the descending vasa recta. I can draw it both ways, but I'm just used to drawing it more the other way. But the bottom line is, as long as you know which vasa recta, which lamp the water enters and which one the salt entered, then you're good. Whatever works best for you. That's probably the best way. Okay? I hope I answered your question. Who had a hand up? Then someone had something up here?
Yeah, but you answered it when
I think I kinda answered it for you?
Yeah.
Okay, so yeah, even, it's a good idea, even to practice, do it both, like to see which one works that you understand better. But again, the bottom line, what we're trying to say again here is that water has to enter the ascending vasa recta. I don't care which side you draw your vasa recta at, the ascending one. And then the descending lamp, that's where the sodium and the solutes have to enter. That was slide 20? Yeah. So again, you understand why this was the most difficult drawing of the whole semester. Today was the special day, okay? We will continue, this is all in words, what this thing, and then we'll continue talking about this and talk about urea and stuff next time. Okay, so I'll finish this up, because I'm not gonna